Okay. In this session, we are going to introduce a new concept of programming in C called functions. Okay. So initially, let us just try to motivate why we need functions, and then we will try to see whether programming becomes easier if we have functions. Okay. So let's say that why do we need functions? There are essentially two different reasons for it, and I'll mention these reasons one after the other. The first reason is to break up a complex problem into simple subproblems. All of us, for example, like to drop to-do lists saying that these are the things I wish to accomplish today. So step 1, get to college. Step 2, attend classes. Step 3, finish homework or something like that. And then each of those main tasks will have several subtasks. In order to get to college, maybe you need to renew the ticket subscription, get on the bus, get to college, and so on. So each of those higher level tasks involves several such smaller subtasks. And conceptually, it's cleaner to say that these are the big level things that I want to do. Each of those big level tasks have several subtasks, so that I can think of it what I want to accomplish in a layer wise manner. Okay. So this is something that we do intuitively. We always break up a complex problem into simpler subproblems, so that we can analyze the simpler subproblem and perform it completely, and then come back to the bigger problem. So we need to solve it each separately, and the main tool for this programming in C, which allows you to accomplish breaking up a complex subproblem into simpler subproblems, is what is known as functions. So this enables you to do what is known as modular programming in C. And functions are not new. We have already seen 3 functions in particular. Main was a function that we always wrote, and then we have printf and scanf, which we use for outputting and inputting respectively. Okay. So let's just motivate the notion of functions by using the second motivation that I was talking about. So suppose you have you want to say I want to compute nck, which is n factorial upon k factorial n minus k factorial, right? So this is the definition of n choose k, or nck as it is known. Now suppose I want to write this, encode this into a C program. So I will have, let's say, a main function, and then inside the main function I will have let's say 3 variables a, b, c, and then float a result, because the result of a division will be a float. So I'll have, what should I do intuitively? One way to do it is, I'll have a block of code which says it will calculate n factorial, which is the numerator. Okay, then I'll say that a equal to n factorial. At the end of this, let's say that a stores n factorial. Okay. Then I'll have another block of code which says that I'll calculate k factorial, and then this will say, let's say, b equal to k factorial. And a third block of code will calculate n minus k factorial. Let's say I'll store this in C, and then I'll say, okay, result equal to a by b times c. Okay, some code that looks like this. And you would notice what is inconvenient about it. All these 3 blocks of code, once we complete it, will look very similar. They are all calculating the factorial of a particular number, but there is nothing in C which will that using the features we have seen so far, which will tell us that this code and this code are essentially the same, and I need to write that similar code only once. Okay, so there is no simple way to use loops to accomplish this. So it seems like this redundant business of writing similar code again and again can be avoided. Okay, so this is the second motivation for introducing the notion of functions, which is basically to avoid duplication of code. Okay, so here is a side benefit of functions: avoid code replication. We've already seen loops to some extent avoid code replication, but here is a newer method to avoid code replication in a greater degree. Okay, so the second reason why we write functions is to avoid writing similar code again and again. So let's try to write functions by motivating it with the help of an example. This example will show the benefit of how we can avoid code duplication using functions, and also how we can break up a complex problem into simpler subproblems. Okay, so in this I'll introduce the problem similar to what we have seen before. We have a sequence of numbers. The first number tells you how many inputs there are, and then what we need to do is to pick out the numbers which are relatively prime in this sequence. So two numbers are relatively prime if their GCD is 1. Okay, so 16 and 7 are relatively prime. 4 and 6 are not, because they have a common factor of 2. 6 and 16 are not, they have a common factor of 2. 16 and 7 don't have a common factor other than 1. 7 and 8 are similarly relatively prime. 8 and 9 are relatively prime. 9 and 10 are relatively prime, and 10 and 11 are relatively prime. So these are the relatively prime pairs. Okay, and we need to write a function which, given a sequence of these numbers, count how many pairs, how many successively occurring numbers are relatively prime to each other. In this case, there are 5 such pairs. So in this problem, we can clearly see that there is a subproblem, which is given two numbers, are they relatively prime? That is one subproblem. And if we have the solution to that subproblem, then we can compose the solution to the whole problem as follows. Given two numbers, I check whether they are relatively prime. If they are relatively prime, I will increment the count of the relatively prime pairs I have seen so far. Otherwise, I will skip to the next pair and see whether they are relatively prime. So for each new pair of numbers I am seeing, that's the subtask of checking whether they are relatively prime. So let's say that, suppose we have a function. A function is something that we will see in a minute. Suppose we have a small component which will perform the task of testing is coprime AB. So is coprime AB, that function will take two numbers A and B and check whether they are relatively prime or not. If A and B are relatively prime, it evaluates to 1. We say that it returns 1 if they are relatively prime, and if they are not coprime to each other, if they are not relatively prime, then it has to return as 0. Okay. So it has to evaluate to 0. Now associated with every function, there are three concepts. We will see them one by one. There is this declaration of a function which says what does the function look like. Okay, what is the type of the function? So the declaration of the function will be written in the following way. It will be written as int is coprime, int A, int B. Okay, this means that is coprime is the function name, and then it takes two arguments, A and B, which are of type int. So int A and int B. if we had written another function which takes a float a and int b, we would say function int float a int b. Okay. So in this case we are taking two integers as arguments, so you have to say int a int b. A small syntactic point that you have to note is that you cannot abbreviate this as int a comma b. So that is not allowed. Each variable needs to have a separate type signature. So these are called the input arguments. Okay, so that is the second part of the declaration. The first part of the declaration, the first, which says that it is an int, is actually the type of the return value. Okay. So the return value is 1 if the pair is co-prime, and it is 0 if the pair is not co-prime. So the return value is an integer. Okay. So we need a function name, we need a declaration of the input arguments, the arguments need to be named, and the return value of the output. Okay. So let us say how do we design the higher level functions. So here is how you use functions when you program. You assume that the function is already available to you, okay, and it does what it is supposed to do. Using that, how do I build the solution to the whole program? So in this case, let us just assume that we have written int is co-prime, we have written that function, and we are interested in how do we build the solution to the entire problem using that. Okay. So how do you do that? You have a flow chart which reads numbers one by one, okay, and count is the number of co-prime pairs that you have seen so far. So you check whether you have seen n numbers. If you have not seen n numbers, then you read the next number and check whether the previous number and the current number form a co-prime pair. So you give is co-prime current, it will return 1 if they are co-prime, so that will get added to the count. If they are not co-prime, they will it will return as 0, so count will remain as it is. Okay. Once you do that, you say previous equal to current and indicate that you are going to read the next number. Okay. This is similar to other problems where we scanned a bunch of numbers and did some function based on that. Okay. The new thing here is the is co-prime function, which we just assume that it is correctly written and it does what it is supposed to do. Okay. So this is the function declaration. Okay. Now how do you code this up? You basically code this up in C, just as you did it with other other functions like scanf. You just say count plus is co-prime previous current. So this is how you can encode the flowchart, including the function call as a C program. Now let us come to the interesting part, which is how do we design the int is co-prime function. So the top is the declaration part of the function, where I say that what is its type. So the function name is co-prime. It takes two variables a and b. A is of type int, b is of type int, and it is supposed to return an integer value. So that much is clear from the type signature, so called, of is co-prime. Okay. Now what do you do with it? You say that so this is the classic GCD code. You declare a t variable. If a is less than b, you swap a and b. Okay. And this part of the code is just calculating the GCD. Okay, this is code that we have seen before, and at the end of that, a will become the GCD. If a and b are co-prime, then a will be 1. If a is any number greater than 1, then they are not co-prime. So if a is equal to 1, you return 1, and for returning you use the keyword return. Okay. So you return the value 1, otherwise you return the value 0. So this is how you write the function isCoPrime. So now we have to put both these code together. So I'll say include stdio.h. This is the first line of the code. Then I will have the source code for isCoPrime. Okay. So I'll write that, and afterwards write main function. Okay. So that when main calls isCoPrime function, then we already have the code for isCoPrime available. Okay, first this line, then the isCoPrime function, and then the main function. So let's look at the function in somewhat greater detail. A and B are what are called the formal parameters of the function. They are viewed as variables. Now the formal parameters are visible only within the function. So we say that their scope is inside the function. Okay. Now there is this is what is known as the definition of the function. Every function can be called. Notice that we have already called the functions like printf and scanf. So once you define a function, you can call a function. Calling a function will be evaluating that function with particular arguments. You can do that. Okay, so when you call a function, you execute the function with the given arguments. So 5 becomes A and 6 becomes B. Once a function call is encountered, what happens is that formal parameters are mapped to actual parameters. So A becomes, so the value 5 is copied to A and the value 6 is copied to B. This process of copying values is known as parameter passing. Then what you do is you store the return address of the call. The return address is the line of the main function where the function was called. So let's say that it was called in the second line of main. Once the function finishes, it has to come back to this point. Now in addition, we also create a box for storing the return value. At the end of the function, either 1 or 0 will be returned. So we also need some space in memory to store that return value. Okay. So to look at it in slightly greater detail, so let's say that isCoPrime 9.4 is called in step 20A. So this is the address 20A, by which I mean it's line 20 and some location A. So now you have to allocate the space for the return value, store the return address and pass the parameters. Okay. Now when you pass the inputs 9 and 4, the space is allocated for A equal to 9 and B equal to 4. This is the process of parameter passing. Okay. So we visualize the memory as a stack. Okay. So when you start the program, you start executing from line 1 of main. So x is initialized to -1, and then you come to the function call isCoPrime 9.4. So when you execute this, you do the following: you allocate the space for the return value, you pass the parameters, and then execute the function, and finally pass back the return value. Okay. So when you execute the function, you imagine that the stack is now divided into a separate space. Okay. So here is a clean separation between the memory that is required for main. So above here is main, and below here is the memory required for isCoPrime. So in that I have stored a box for return value. I have stored the return address, which is 20A, and then I have A equal to 9 and B equal to 4. Now I will execute the function as though memory is limited to here. Okay. So I will declare T and then execute the GCD algorithm. Okay. So this is stuff that we have seen before, and finally A is the GCD, which is 1. If A is 1, we have to return 1. So the value 1 will be copied to the return value. Okay. And that is the value that will be passed back. So x will be 1. So the return value will be copied back to the main function.